All right. So, what has happened? Um, Basically, I have done the NFA stuff, I think, and cleaned it up and made the code structured correctly. From yesterday, the bug. I might have let. Oh, did I not keep it? Oh, okay. Hang on. Size of. Okay, I think it was. Oh, that's a few times. One of these, instead of writing size of NFA, I had written. It'll be recorded somewhere in the video. I don't know where, but it might have been this one. It was like the first 80 lines or something. So, but it's different now because of the. Okay, okay. Well, it'll be less than 80. It'll be like before. It might be here. In like translate expression or something, I had written size of base. Like I had written size of and then put the variable name instead of NFA, which meant that only 8 bytes were allocated, which is why there was like weird errors of like, oh, I'm trying to use memory, but I can't use the memory because there wasn't enough space basically to put in all the fields. So I think like trying to be trying to use the 8 bytes to store all of the NFA information because the NFA information is like two integers and two node pointers. So 8 bytes, and then a 4 byte integer. So that's what 16 plus 4, 20. It's 20 bytes of like information. It tried to squeeze it all into 8 bytes, and then it was like I can't align things correctly. That's why that error was coming. And I think from the debugger as well, we saw that like it was only allocating 8 bytes or something. And I was like, what's going on? And so I read my code carefully, and I was like, oh, that is why. So I would have recorded myself typing base or whatever size of some pointer. So that's fun. But that was the bug. So now it seems to be working. I ran some test cases. Yep, I ran some test cases, and there's these 11 test cases, including the empty. Ran through them, printed out like the information about the node, about the graph, and then drew out the graph, and made sure that the graph looked correct. And so, like for example, if I take this one, A or B star, you can see like the OR effect. Like you either go up to get the A, or you go down to get the B. And then for the B, you also have this looping stuff because you can either, completely skip the B, going from 4 to 5, because it's B star, right? 0 or more occurrences. So you can skip the B completely and just go to the end. Or you can sort of go through, hit the B once and go through, or you can hit the B once and then loop through a few times and then go to the end. So that's the 0 or more occurrences of B. So there's two parts. So that's where the OR comes in. So that kind of I was very happy with how it looked for every graph. This was the most complicated one, and that one seemed to work out as well. You can see like it's like 3 ORs: A, B, or C, D, star, or F, G, and we kind of have 3 ORs going 1, 2, and 3 down here. So pretty happy overall. What happened? What was over here? Oh yeah. Then I just worked on like making sure there was no leaks in like memory leaks. So I had to basically I did a for some reason I changed it from a D. I could have done it with a DFS actually, but I had a DF because I had DFS for like printing stuff, right? But I rewrote it using a BFS to free all my stuff. It's in here, wouldn't it? It was in here. So basically, I have a queue. Node queue is a dynamic array. You can see over here. This is using the macro over here. So I made a queue. That's a dynamic array. I very scrappily basically use a index to basically keep track of where I'm up to in the head of the queue, where the head of the queue is. And then while that head is smaller than the size, we go through, we visit all the neighbors, we check have we visited this neighbor yet. If not, then we mark it as visited, and then we append the neighbor to the queue. Typical BFS stuff, sorry. And then the idea is the point of this BFS is to free just all the edges in the graph. Because I had like I was freeing nodes. I had like free current in here, where current is like the current node I'm up to. But that had heap use off a free errors. Like it triggered the address sanitizer, because when you do the BFS, like I worked through an example, but like for example, I think this was a good one, yeah. You go from 4 to 0, you go from 4 and then you get 0 and 2, and then from 0 you get 1, and from 2 you get 3, and then from 1 you get 5, right? That's like how the queue would work. So 4, then 0 and 2 both get queued, and then from 0, 1 gets queued, and then from 2, 3 gets queued, and then from 1, 5 gets queued. If you free visited, the risk becomes like, let's say 3 had like one more edge for some reason before it got to 5. Let's say there was like 6 over here and then 5. I don't know why this would happen, but let's just for example, right? What would happen is 1 would NQ 5, 3 would NQ 6, and then 5 would NQ nobody. And then if I had this line, if I freed the current, did I delete it? Yeah. If I freed the current, then 5 would get killed, right? 5 would get freed. Then 3, which had queued 6, so 6 would now be the current, and it would look for neighbors, which is 5. And that is true because this edge still exists. The 5 has been freed, but the edge, which has been mallocked, is still existing. So when I'm looking at the neighbors of 6, we would see the edge, and then I would want to check if that node 5 has been visited yet. So I would run this to get the neighbor ID. But the issue is current edges data ID all exists, but when I try to access the neighbor object, that's been freed. I freed it because I accessed 5 from node 1. So this has been freed. When I do this line from 6, where 6 is the current, when I run this line, accessing neighbor is illegal because I freed it already. So then that caused errors. So I can't free the nodes during the BFS, but that's all good. I can free all the edges. And then the idea is the queue that I amassed through the BFS has a list of all the nodes, because BFS visits every vertex as well as every edge. So in that sense, I have a list of all the nodes anyway. So when I finish my my BFS and I free the visited, I can firstly just I can iterate through all the nodes in the queue. It's not really a queue at this point. I'm just treating it like a simple array. But I can iterate through it and free all the queue data I, which is basically all the nodes that I've stored in the queue. Then I can do node queue free, which was just an additional function I made in my dynamic array macro, and then I can free the actual NFA. The other freeing efforts I did was during the actual construction, because you can imagine the original point of this diagram was we understand that the NFA structure that I've used is you have the NFA object, which has a start and end node that is associated with it immediately, and then within the nodes you have edges and stuff. But in order to construct this outermost NFA, in most cases I'll have to construct a bunch of smaller NFAs that inductively build up to the larger NFA. What I didn't realize yesterday and what I've clocked today is that I wasn't keeping track of these NFAs at all. The smaller ones, the sub NFAs. I was sort of using them and then using them to build the bigger one, and that was cool and was correct, but I was losing track of all the NFAs, which means all this memory, all these NFA structures that I was mallocking weren't being freed and weren't being stored, so I had no way of accessing them. So what I did was, for example, if I look at like a simple one, I think one of the bottom ones is probably easier. I think this one's probably the easiest. Star expression. Star expression, remember, starts with star expression is a simple expression and then an optional star. So it's the looping one. It's the looping graph, this guy. So you build the mini NFA and then you build 2 new nodes and then insert a bunch of structures, a bunch of edges, sorry. build a smaller NFA, and then 2 nodes, and then a few edges, right? So this is us creating the simple, and this is us creating the simple translate. This is us making sure there is indeed a star, because it can be empty, of course, but we make sure it's a star. From there, we create the base NFA, which is the, the parent. And we do all this, we do all the linking, as we saw in the video. And I didn't have this line before, where I free the child NFA. Once I do all the linking with the edges, I don't actually need the inner NFA anymore. I don't actually need that object. I need the nodes in there, but freeing the NFA alone will not free the nodes and stuff associated with it, the start or finish nodes or anything. So I just free that pointer, so that gets freed and that's cleaned. And then I only have one sort of currently active NFA object I have to be worried about any one time. So I do that for each function, each of the translate functions. That way I make sure that I only have one NFA that I'm dealing with by the end of the construction algorithm. And then from there, I ran this, my leaks thingy-majiggy, and I was running on some pretty random test cases. Some stars in there. Is that fine? Yeah. The program does hang a touch, but I think that's only after it sort of gets through the construction and then it's like doing the memory leak stuff. But yeah, generally speaking, seems like no memory leaks. So that's pretty much where I got up to. Oh, the only other thing was I added static inline, because when I tried to, when I did all this, header file stuff, and I had 2 source files for the NFAs. Of course, I also have all my source files for the parser. Oh, this is the wrong place. Oh, no, it's right. My source files for the parser and all that. When I tried to split it into headers and stuff, I got an error for duplicate stuff, like duplicate tokens or something. I'll get rid of this so I can show. Let me compile. Bang, like that. So you can see I got rid of the static inline thing for append. So you can see that edges append, node q append, edges append, node q append, like the append functions got like this duplicate issue. So I learned a little bit about the static stuff. Let me just first explain. So there are these 2 types I've created, edges and node q, which rely on the dynamic array macro, right? Declare dynamic array macro, where basically, edges is going to be a dynamic array which holds a bunch of edge pointers, and node q is going to be the dynamic array that holds a bunch of node pointers. So edge pointers, node pointers. And the idea is when you do this, remember that what a macro is it's basically a copy and paste and replace. Like when we run this line, what we're telling the compiler is I want you to copy basically this entire template into here, replace this with this entire template, and then anytime you see type, replace it with edge star, and every time you see label, replace it with edges, right? Label being the name of the struct, right? Using the type def. So when we don't put static, when we're just doing this, and we include, well, first of all, we run this, but we then include nfa.h in 2 source files, here and here, what happens is that copy paste job basically happens twice. And I was under the impression that the header guards, like these guys and these guys, would solve all the problems. But basically that copy and paste and replace job happens here, but then because of this hash include, the entirety of the NFA stuff gets copied into here and then also gets copied into here, which means the copy and paste for these 2 declare dynamic array instances happens in NFA construct and NFA free, which is why, without any other modifications, we see duplicates because in the source code, it literally appears twice. The compiler, I think it's the compiler, is basically copying all of this stuff into two source files. And of course, that's a bit of a problem because it feels ambiguous. Of course, it's referring to the same stuff, but we have two definitions for the same thing, so there's a problem. So what static does, as far as I'm aware, I'm not super comfortable with all like this whole I read these keywords like translation unit or compilation unit or whatever, which is basically essentially my understanding is it's like the different source files after all this copying and pasting has been done. So when you don't put static, my understanding is the function, for example, this append function, when you don't put static in front of it, that function is understood to be, I guess, global, sort of accessible from any of the source files. Like you might have defined it in here, but then of course, after the copy and paste job, you might have defined it in a particular source file, but it's available and free to use or visible in any of the source files. Which is why if you see two definitions, there's a problem because it's like, oh, which one do I use now? If I've got two definitions in two source files, then what do I do? Using static, essentially tells, I guess it tells the linker that, maybe the compiler as well, I don't know, tells somebody that the function should only be used in the file it is declared in. So that means you can declare and define, I guess, this function twice, here and here, but because you are basically promising that these files will only use their version of the function by this static thing, it is not possible for these two files to see the other person's function definition. And therefore, even if you have duplicates still, the ambiguity is gone. And so there's no problems. So I think if I compile this now, there's no problems. The inline thing, I think I just added because it was like just there. But I don't know if it's actually necessary. I forget what inline even does, to be honest. What does inline do in C? Not C. Maybe. Yeah, this was like, it was like a nice to have. So I don't know if it's actually necessary, but yeah, the major thing was the static. The static was like, oh, I've never used either of these before in C. So I was like, oh, I don't know what this is. So I got to do a lot of Googling. But yeah, that was pretty interesting. The inline is, I don't know if I should actually know this. Wait, let me just read this real quick. Eliminate the overhead of a standard function calls, such as saving registers, pushing arguments onto the stack. Okay. When you mark a function as inline, you're suggesting that the compiler replace the function call directly with the function code body. Oh, right. So instead of calling the function, which I do a few times, like edges append, if I mark it as inline, I'm literally just replacing that one line with like these 7 lines, whatever, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, not even close, with these 10 lines. Okay, so yeah, inline has nothing to do with the duplication error. I must have just included it because I was like, lol, whatever. I guess, yeah, like for some functions, if it's like one-liners, but I just wanted like a better name, then yeah, I guess inline does make sense. Okay, that's also good to know. But yeah, the actual, what fixes the problem of the duplicate things is the static, because it keeps the, I guess it's kind of keeping the, from the linker's perspective, it keeps the function privatized to a particular file, is how I kind of understand it. So yeah, that's me learning stuff, so that's cool. Now it's 10:45. I'll do this for like maybe an hour at most, just because I don't want to sleep too late. But I'm pretty like gassed, as in happy, because this NFA thing worked a little bit better than I thought it would, to be honest. I thought I was gonna like really bomb this, but it's actually going okay. So the next step in this regex, sorry. The next step in this NFA, in this regex business, is translating the NFA into a DFA. So we're about like, I'd say 2/3 or like 3/5 into like the prep work. And then the DFA is kind of like the last major step, and then we can sort of write the thing that will do the actual matching. So I have my notes, I think. So study session number 1 was for the NFAs and Thompson's algorithm, Thompson's construction. The second one is about DFAs and subset construction. So the way to introduce this is, from last video, we saw that NFAs is basically a graph with 2 major properties. Each node can have 2 outgoing edges with the same symbol. So, for example, if I have a node 1 and it's going to have outgoing edges, if I have an A and another edge with an A on it, that's completely fine. For an NFA specifically, that's completely fine. And an outgoing edge can have the empty string or epsilon coming out of it. So again, I don't know if I made this very clear, but the epsilon symbol is basically equivalent to the empty string. Like, we just use epsilon because I guess it's like a nice symbol, like a single character that we can use to represent the empty string. But it's equivalent. Like it's like a null symbol kind of thing. So outgoing edge is allowed to have the empty string, right? And in our context, the reason why we're so interested in NFAs is because we can translate a regex like ABC into a kind of graph. Where the idea is, given a particular start node and a finishing node, the graph will match a pattern. The graph itself, the NFA, will match a pattern if there exists a path from the starting node to a finishing node, a double circled node, that spells out the word. So if, for example, so this is the regex, the corresponding DFA, the NFA, sorry, might look like this. So if I had some text that was ABC and I passed it into this graph, starting from here, I would say, here, I can get to A, I can get to B, and then I can get to C, and I can get to the finishing node using a particular path. But if I had text like ABD, then it's like, okay, I can get through A, I can get through B, but it's like, oh, I have a D now. I have no edge that lets me, traverse through D. So there's no path. So this one's good, this one's not. So in that sense, we can translate a regex expression into a graph that can then be used to check, is there a path that lets me sort of cover this particular bit of text. So it's kind of step 1. However, the issue with using an NFA straight away is the fact that it allows for these epsilon edges and the fact that it allows for, objects with the same edges with the same symbol. Because, for example, if I take that same kind of drawing, 1, A, and let's say, whatever, my text is like blah, 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 some stuff, and then an A in it, blah, 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 more stuff, right? Let's say I traverse through the front half here and I eventually get to node 1. I see this A and I'm like, okay, I kind of have 2 options that I can take. And, for 2 options, that's not so bad. You can try one way, see if it works. If it doesn't work, backtrack, try again. But, an NFA could have a whole bunch of like thingies, A edges, right? Edges marked with an A. So it's a little bit, you risk it getting a little bit annoying, I guess, computationally. Of course, writing it maybe won't be a huge deal. You just, use sort of a recursive backtracking thing or do a kind of stack thing or whatever. And that's cool, but do you really want to have to deal with all that backtracking? And, at least in the sort of lectures that I've watched, the answer is no. So this is where we get to DFAs, which is a lot more strict about the kind of rules about the graph. So while NFAs allow for two outgoing edges to have the same symbol and allow for an outgoing edge to have the empty string on it, a DFA is the exact opposite. No two outgoing edges of a particular node can have the same symbol, and no outgoing edge can have the epsilon on it. So, you know, if I'm going to have edges going out of a particular node, the symbols on them should all be different, right? And you are not allowed to have an epsilon edge. This is illegal. Shouldn't have, right? And if those two properties hold for a particular graph, then you have a DFA. Okay, very cool. And so that's the idea, and the D in DFA stands for deterministic, kind of because of that example I showed, where it's like, if you only have one instance of a particular edge, like one instance of a particular symbol on a particular edge for a particular node, then there's no choices for you to make. You just traverse. Either there's an edge that you can traverse or there isn't. There's not like multiple choices that you can take, and there's no backtracking you'd have to do. So deterministic is only one option, one answer every time. So yeah, the algorithm that we use to convert an NFA into a DFA is called a subset construction algorithm. And to motivate it, I think it's easiest to go through kind of an example, see kind of what the end goal is, and see how it kind of relates to the NFA before we talk about the very specific sort of implementation details. So suppose you have a regex that looks like this. This was taken from my uni lecture, so I don't know if they'll get me in trouble, but whatever. So, you know, you're either looking for if less than or equal to, or this just means like any letter, any English letter, basically, uppercase or lowercase. This means any letter, uppercase, lowercase. This means digit. And what it's specifically saying is, if I was to write it, it's letter followed by either a letter or a digit from 0 to 9 repeated. That's all this is saying. And the idea is, so yeah, if the if keyword less than or equal to, or an identifier. So you think of code, like when you write a variable, it has to start with a letter, and then it can be like as many letters and numbers as you want. Right? But it has to start with a letter, which is why we have like the first group, and then in brackets we have 0 or more like letters and digits. So these are the things we're trying to sort of match. You know, if we pass in a particular bit of text and it happens to be one of these four things, either an identifier, if less than or less than or equal to, then it should say, you know, matched or whatever. So the NFA, we would draw something like this. We would have the starting node, the finishing node, and then, you know, it's a bunch of ors. So we would sort of branch it into, we would have sort of four options to go from the start to each of the, you know, this is saying n if, which is like just a way of like generically saying whatever the graph where if looks like, you know, just it represents n less than equal to n id. We saw this sort of notation or whatever when we were describing the Thompson algorithm. So it's the same idea. And then more specifically, rather than saying this abstract generic thing, we can actually write the particular NFA. So very similar structure, except I'm actually writing, or I'm actually drawing the NFA rather than just like abstractly doing it. So for example, and if I want to match the if, I would go up this branch and then go I, F, and then down to the finishing node being the double circle. If I want to match the less than, I would go here and then go less than and then go to the end. Notice that I'm allowed to basically traverse the epsilon edges without like affecting the matching or anything, because epsilon means nothing. I'm not really adding any text or anything. If I want to match the less than or equal to, I would go down to here, right, and bang. And then if I wanted to match any identifier, I would say, hey, look, I can go like down this way, and then there's a self loop here, get as many letters or digits as I need to make it match, and then get to the end, and that would be the end, right? So again, just to really drive this point home, imagine I was matching less than or equal to, right? That's my text. From here, like, there's two paths you could possibly take. You could either try going this way, and this would sort of take you somewhat far, but then you wouldn't be able to match the equal sign, right? You would match the less than, but then this wouldn't work. So you would backtrack, and then you would go down to here, and then it would work. You know, over here, you would sort of half-heartedly try this, and then, oh, that's an I, that doesn't work. Down here, you would try this, oh, letter, that's not really a letter, so backtrack. So, you know, there's a fair bit of that, because of the epsilons, you know, you kind of have to try a few different parts, and because you're allowed to have kind of this repetition of like the same guys, you risk kind of traveling down a particular path a bit more than you should, and then, oh, it's wrong, and then you have to go back, and then you finally find the correct path. So that's kind of why in NFA we kind of are thinking about translating it to a DFA instead. Right. So DFA, again, I haven't explained how we get to this, but this is what a DFA looks like. What I want you to notice is the nodes of a DFA contain the nodes of an NFA, right? So S1469 refers to S1, 4, 6, and 9. Like, it's referring to those nodes. Why it refers to those nodes, we'll talk about, but yeah, each node of the DFA is basically containing a set of nodes in the NFA. 5, 7A referring to 5, 7, and A, the acceptance or finishing node. Notice how for each one of these nodes, they have outgoing edges, like this and this, for example. Notice how there's no epsilon edges, is the first thing. And secondly, you know, if we focus on this node, for example, this edge is completely disjoint to this edge. We say, you know, this edge is I. This edge is every letter except I. So if you want to, you know, if you were matching I, X, D, for example, this should match the graph because of the ID version, right? It matches the ID thing. So it should match. What we would do is we would go start from here, and because it starts with an I, we would definitely go here. There's no contest, you know, there's no ambiguity. Oh, should I take the I or should I take the letter? You know, like, there's no ambiguity. I'm definitely going this way. And then from there, I see an X. So from here, I'm like, oh, there's an X, which means I should go down to here, because this edge is digits or letters besides F. So it's a digit besides F. You know, there's no way I would take this. There's no way I would traverse this edge because it's an F. And then there's a D, so I would, from here, I'd say, what edges can I use? Oh, there's this loop here. So I'll do that once, and that will hit the D as well. So all three letters are a thing, and then we see that this is a double circle, so we're allowed to finish here if we want, and we will because we're out of letters. So there is a legitimate path to get from the starting node to a finishing node. Notice how there are multiple finishing nodes. In fact, all of them are finishing nodes besides the very first one. Besides the start node, this is not a finishing node, all the other ones are. And the way we kind of, without going into implementation details yet, notice how the finishing nodes are the ones with the A in them. The start node doesn't have the A in it. The finishing nodes all have the A, which is the node that was the finishing node in the NFA. So that's a pattern to sort of notice. If the node contains an NFA finishing node, it itself will be a finishing node in the DFA. So just to, you know, for now it's just a pattern to recognize. So these are the observations. So each node is labeled with one or more nodes from the NFA. Outgoing edges from a particular node is always a different edge, has different edge labels. No two edges have the same edge label. No edge has the empty string, no epsilons. The start node is the one with the NFA start label in it, so the start node is the one that has the S, because that was the start node in the NFA. And terminal nodes in the DFA are the ones which have an NFA terminal label in them. So what I said before, you're going to be in the DFA, you are going to be a terminating node if you contain at least one NFA terminating node. Loosely recall that in NFAs you can have multiple finishing nodes, but in Thompson's algorithm, I think you never do. I think you only have one. But in general, there could be like A as one of the finishing nodes. You could have like B as well, for example, as another one. So, you shouldn't always expect there to be only one. Okay, now we discuss the subset construction algorithm. So before we can get into the exactly how the algorithm runs, we should discuss sort of the operations that are done in the algorithm. So we have this idea of epsilon closure. So the way I'll introduce this is by saying, imagine you consider one of the nodes in the NFA. So in the NFA, just think of one of the nodes, and you want to ask the question, if I'm only allowed to traverse epsilon edges, what nodes can I reach? That's the question. So as an example, if we look at the S state in the NFA, so looking over here, we ask, from here, what nodes can we reach using only epsilon edges? So we're like, okay, from here I can go to here. So I have 1, for example. From here I can go to here. That's 4. From here I can go to here. That's 6. And from here I can go to here to get to 9. For example, if there was another node like 11 over here, which was epsilon, then that would count as well. I can get to 11 using just epsilon edges from S. I can go here, and then that. I can get to 11, so that would count. And S itself we kind of include as well in the closure set. So that's the question. I can keep this actually. I'll get rid of the 11. So 1, 4, 6, 9, and then also we kind of include S, because you can get to S using epsilon edges. You just don't use any of them, right? You just use 0 edges. So that's kind of my epsilon closure of S, we say. So what is the, S1469, oops, forgot I had the pen selected. S1469 is the epsilon closure of S. So that's one operation. And then also note that epsilon closure can be applied to a set of nodes. Similar idea can be applied to a set of NFA nodes. So what is the epsilon closure of S and 5? So not just S and 5. So we look at each node in the set and we ask, what nodes can we reach via epsilon edges? So for the S, it'll be the same, 1, 4, 6, 9. And then we also have to look at 5. From 5, we can get to 5, of course. We can easily get to 5 because we don't traverse any edges. And then we can also get to A. Right? So in that sense, it should be S5, 1, 4, 6. That should say 9, not 8. Right? Yeah, that's a typo. Unless I am bugging out, but 8 is 8 is over there. Definitely 9. So 1, 5, S and 5, and then 1, 4, 6, 9, and also A. Okay, so that's what epsilon closure is. We use that in the algorithm. You'll see it being used. And just a note I highlight, it is the use of epsilon closure that allows us to remove epsilon edges. Just in case anyone's wondering how these properties come about, these strict properties of the DFA come about, it is the use of epsilon closure that lets us kind of essentially make two states somehow equal each other. We say they're kind of somewhat equivalent because from one you can reach another using the empty string without using any symbols. So in that sense, we get rid of epsilon edges. And then move operation is sort of the next operation. So consider one or more nodes in the NFA and some particular symbol. And we just ask, from these nodes, what nodes can we reach via edges labeled with that particular symbol? So, for example, what nodes can we reach from nodes 4, 6 using the symbol less than? So we said from 4, 6, so let's get rid of some of this red. Come on, there you go. Shouldn't have highlighted all this so rigorously. Okay. This is like, there's no way I can delete. Yeah, I'm gonna have to just erase the edge. Okay. So what's the question again? From 4 and 6. Okay. So we are applying the move operation on the set 4, 6 using the symbol less than. This is like me applying the operation. So looking at, no, I shouldn't have written it down here. So looking at 4 and looking at 6, we ask what nodes can we reach using just one less than edge. So it's not like as many as we want. We only look at like the nearest, like the neighboring nodes. So I've clearly rigged the question to make it simple, but from here we can get to 5, and from here we can get to 7 using less than edges. So the answer to this is 5 and 7. Notice that 4 and 6 aren't included in this because you know, you can't get to 4 from 4 using less than edges specifically. You can use it doing nothing, but you can't get there using less than edges specifically. So there you go. So yeah. What did I say? I shouldn't delete. I don't know why I deleted it. 5 and 7. So that should be the answer to that. 5 and 7, yeah. So, and it's the use of the move operation that prevents two different edges from the same node having the same label. So that's how it is this operation that allows that second property to come about. We essentially ensure that if you can get to two different edges, if you can get to two different nodes from two different edges that are labeled the same, we will somehow combine them into one set, and you'll see we'll make them into one node as well. Okay, so that's like the theory behind like the operations that are used. Now we can discuss the algorithm. So initialization, we want to take some start node, the start node, there's only one start node. We want to take the start node from the NFA, call it S, find its epsilon closure, so figure out all the other nodes you can reach using epsilon edges, and mark this resulting node as the start node for the DFA. So for example, what did we say? We said the epsilon closure of S is equal to S, 1, 4, 6, and 9. Therefore, the start node of the DFA should be S, 1, 4, 6, and 9. And that's what we see in here. That's how we get this start node. It is the epsilon closure of the start node in the NFA. Okay, so that's the initialization. And we're going to mark this node as unprocessed. What unprocessed means is we haven't really processed it. That's hard to say what it means just yet, but we'll see. But mark it as somehow not used yet. So what the loop part of the algorithm is, while we still have an unprocessed node, which we will definitely have at the start because we have the starting node. So while we still have an unprocessed node to work with in the DFA, calling it X, take this node, this DFA node, it's a DFA node, right? Take this node and do the following. For every possible symbol A, okay? And when I say every possible, I mean every possible symbol. Like, even if it's not necessarily in your regex, every possible symbol in your language. Letters, uppercase, numbers, any symbols that you think you might going to be using. You kind of want to go through all of them. We'll discuss that a little bit more, but for now, just imagine you're going through every single possible symbol you could work with. It's just kind of safe in that way. And the idea is, for that particular node, right, in the DFA, and for every particular symbol, try to apply the move operation using this node and with this symbol to get the set Y, right? That is the nodes that can be reached from X via A, via symbol A. So what does that mean? For example, let's say I'm looking at this. So this is my node, for example. This is my unprocessed node. And I'm saying, okay, let's apply the move operation on this particular node, this guy, and let's use symbol I. And the question is, what nodes can I reach? Again, using the NFA, what nodes can I reach using the symbol I? So what I would do is I would go through each individual NFA node written in here and ask, where can I go via the symbol I? So for S, how do I want to say this? For S, I guess there's not one. We don't really have to worry about S. For 1, I can get to 2. Right? From 1, I can get to 2 via an I. And don't forget, from 9, you can get to 10 because I is part of the letter thing. So I can get to 10. So since 9 is in, the start, I have to consider that traversal as well. So that's the output of that move. And then the extra step, after I do that, you do the move operation, expand this output set, Y, expand it by applying the epsilon closure onto Y. That is, okay, we managed to get the 210 because that's the nodes I can get to via the symbol I, but we expand it by doing epsilon closure on these guys. That is, what nodes can I reach using just the epsilon edges? So from 2, I can't get anywhere, there's no epsilon edges, but from 10, I can actually get to A via this epsilon edge, and therefore I need to actually include A in the overall set. So therefore, it should be union actually, not plus. This is the final thing, and therefore, notice how for the I edge, from the start, I have 2, 10, and A. Right? That is the node I have created by thinking about the symbol I and doing this. So for all the other letters, like move from a particular, again, we're thinking about this. If we tried X, for example, another letter, well, from S I can't get anywhere, it's all epsilons. From 1 I can't get anywhere, there's no X. From 4 I can't get anywhere, from 6 I can't get anywhere. From 9 I can get to 10. Oh wait, sorry. So move of the node using symbol X, I can get to 9. Sorry, I can get to 10, I can get to 10. I can get to 10. From 9 I can get to 10 via X. And again, we have to apply epsilon closure on the result as well. So union, we apply epsilon closure on just the 10, we can get to A. And so 10A becomes sort of the node that we draw from here to here. Letters besides I, because of course, if it was X, if it was Y, if it was G, if it was L, if it was M, if it was N, if it was O, if it was P, whatever letter it is, besides I, would always take us to this node. So we can kind of just, really, you might actually be creating a whole bunch of edges for all the different letters, but we just summarize it saying letters besides I. And you'll notice that if you were to do the move operation on this particular state, for all the digits, letters besides i's, for all the digits, all letters besides I, you would get this result as well. But let's say for 210A, this node over here, let's say we apply the move operation. Oh no, sorry. we apply the move operation using the character F, the symbol F. So, like I said, imagine we're focusing on this node now as our unprocessed node, and we're looking at F. So 2, where can we go? We can go to 3. Okay, that's pretty cool. From 2, we can get to 3 via F. From 10, we can get to itself via F. Right? Don't forget the self loop. We can get to 10 from 10, so we have to write that down. And then 210 from A, we can't get anywhere using the F. But then, of course, from 310, we also have to do the epsilon closure. So from 3, we can get to A. From 10, we can get to A, so we include the A in there. And so that becomes the set. From 210A, we draw with the edge F, we get to 310A. So that's why you can kind of see that, each node in the DFA is actually a set of states in the NFA, because we're actually kind of combining what states we can reach from a particular set of states. What states can we reach via a particular symbol? And also this epsilon closure idea of like, what states can I reach using the epsilon edges? So that's that part of the algorithm. Where am I? So yeah, what did I say? We have the start, which is the epsilon closure of the start state in the NFA, or start node. Mark it as unprocessed for every unprocessed node that is still present in the DFA. Apply that for every symbol, for every unprocessed node, for every symbol, use the move operation to get the Y set. That is what nodes can be reached from a node in X via symbol A. Expand the set using the epsilon closure on Y, on this output Y. So the states that can be reached via the empty string. If this node already exists in the DFA, simply draw an edge from X to Y, the output Y, labeled with the symbol A, the particular symbol that we were considering. If the node doesn't exist, then create the node, of course marking it as unprocessed because we haven't touched it yet. Create that node using the Y as the as the annotation of the node before drawing this edge. Okay, so what's happening is, for example, let's say S1469, we're looking at that one because that's the first unprocessed node. We consider all the edges we have to draw. So the nodes we would have created was 210A with the edge I, and 10A with the edges letters besides I. So now when I consider 210A, sorry, when I consider this node, I'm going to be looking at all the digits and letters besides F as the symbols, right? When I do the move operation on this node, with these symbols, my output will be this node, which I've already created because of doing all this. So there's no need to create this node again. All I have to do is construct the edge. There's no need to construct the node again. Okay, I can save some space. That's all that was saying. So, if the node doesn't exist, then of course we have to create the node before we create any edges. Otherwise, just create the edge straight away and label it with the accurate symbol. And we do that all the way around. And the last little detail is if the Y, right, if the particular node that you just created or are considering, if it has a finishing state in it, like A, from the NFA that is, an NFA finishing state in it, then it itself, that overall node itself, should be marked as finishing. So since this guy, for example, had an A in it, this guy should be marked as finishing. It should be double circled. And that's what this last thing is saying. If that node Y that you are, that output node, if it has a finishing node in it, an NFA finishing node, then mark Y as a finishing node itself. And once you've done all that, once you've considered that x and considered every symbol that you could possibly have and try to do the move operation for all the nodes, all the NFA nodes in x using all of those symbols, only then can we mark x as processed. And we do that for every node that we have created in the DFA until all the DFA nodes are processed, and then we are done. We would actually have our DFA graph. I don't know how much sense that made, but the generic idea is that we can kind of think of certain states as equivalent if they are joined by epsilon edges. Like if I can get from S to 4 via just an epsilon edge, then like from a regex perspective, what's the difference between being at state S versus being at state 4, or node S versus node 4? Like the only thing separating them, if the thing that's separating them is an epsilon, then it's like from a text perspective, like they're the same. Like you can keep them as the same, which is why that epsilon closure idea is very powerful. So being at S versus being at 1 versus being at 4 versus 6 versus 9 is the same. It's all the same because all you did was traverse an epsilon edge. It's not very significant. From there, we kind of apply similar ideas to be like, okay, getting from this node to this node, getting from this node to node 2 via I is the same thing as going from this node to 10 via I. Because like you're doing the same symbol, and we're kind of considering all these guys as equivalent. So you can kind of consider this whole set of states as one kind of thing. And you know, if you work through some examples, like if I want to work through less than or equal to, notice how, you know, less than would get me from here to here, and that in itself is one of the parts, right? That's like just going straight from S to 5 and going through to A. Like that path is explicit. Or maybe I want to take the bottom path, 6 going to 7. Both of those options are available, and then from 7 we can get to 8, which is sort of the equal part, less than or equal to. So this algorithm is very clever in the sense that it is able to cut away all of like the common, I guess, prefixes, like the less than symbols, in two separate parts, and actually sort of merge them into one path, where the less than is kind of a prefix path to the less than or equal to. So that's quite cool. Now, how we think about this in code is a bit tricky. Well, not tricky. Well, yeah, a little tricky. There's certain bits to it that I've been thinking about. So implementation. Symbols in the actual text. So this is where this whole idea of, for every possible symbol of A, I need to get rid of some of this. For every symbol, like, because for example, right, at first I thought, okay, if my regex only has 3 letters in it, A, B, C, A, B, C, A, B, C, or whatever, then surely I only have to care about those 3 symbols, A, B, C. Like, I only have to, you know, because the graph itself will only have A, B, and C in it, so what's the point of trying other symbols? The point is, especially for this regex context, is the dot. Remember that the dot refers to a wildcard, right? If I have B dot D, this thing should match bad, it should match bed, it should match bud, it should match BXD, whatever that is, you know? It should match BLD, it can match B less than D, it can match B equals D. You know, this guy should match anything, so long as it starts with a B and ends with a D, then it has one character in the middle. So this idea of, oh, if the regex only has a B and a D in it, I only care about symbols B and D is not true at all. In fact, it's possible to care about any and every symbol. Now, granted, I think that's only true when you do have dots, like full stops or periods. If you didn't, if your regex looked like this, then maybe you could get away with only caring about the symbols in here, and that could be some kind of optimization idea. But since in the worst case, I might have to care about every single symbol, I think it's fair enough just to care about every single symbol all the time, at least for now, just to get this thing working and correct. So that is why I've come to the conclusion that I need to be very considerate about, oh my god, I have to be very considerate about what my symbols are. So, you know, all the letters, all the digits, some white space, all the different kind of random symbols you can get. And basically my my eventual idea was, can I just iterate through like the ASCII table and do it that way? The answer, strictly speaking, is no, because some symbols aren't on the ASCII table, like \S is meant to be a symbol that matches any whitespace character. But we can kind of think of those as add-ons to the ASCII table, things that we sort of try or iterate through after the ASCII table. The ASCII table is a good basis or a good start. I don't care about this example, I don't think. That's fine. So yeah, but this I'm not too worried about. I think so long as I just think about all the symbols that I could possibly be using, I'll just iterate through all of them, but that's my decision. A stack will be used to keep track of the unmarked states. Basically, you can kind of think of it as how we use it for a DFS. On the stack, we will put like whatever nodes that we build, any new nodes that we construct, we'll put them on the stack. And then if it's on the stack, it means that it hasn't been processed yet. So we will pop off the stack and use that node to run the loop again from the algorithm. We will use that particular unprocessed node in the DFA to run the algorithm. So we can use a stack there, that's cool. For the NFA, create a hash table, simple array, indexed by node ID, so that I can easily find a node and its edges. So right now, all I have for my NFA is easy access to the start node, easy access to the finish node, and then like I have to basically do some kind of traversal to actually access all the other nodes, which is annoying because you can see, for example, like if I want to do a move operation, on S1469, I have to look at node S, then I have to look at node 1, and then node 4, and then node 6, and then node 9. And see, you know, are there any edges with an eye in it, got with an eye on it, right? It's annoying to do that if I have to do a DFS every time, you know, that's kind of silly. So having a hash table or some kind of lookup table where I can just easily find the node, because they are indexed, right? S, of course, will actually be like 0 or something. S and A will actually be numbers in my implementation of the Thompson construction algorithm. So they've all got some kind of unique ID, and assuming I don't have like a stupid number of nodes, it should be completely practical to just have an array that is indexed by their IDs. So easy lookup, so I can find the edges really easily, find those nodes and the edges really easily. What else? So the hash table. Okay, so the edges, obviously, when I do this whole move operation with a particular symbol, or even epsilon closure, I have to be like, okay, let's take the same example. I'm looking for what states I can reach using symbol I from S1469. When I look at symbol 9, let's say, or if I look at state 1, in this case it's not a big deal because there's only one edge, but imagine there was like 15 edges, then, you know, I have to iterate through 15 edges before I find the edge I want that actually has a symbol I on it. So the fact that I have a very simple, unordered and unprocessed list array that stores the edges for a particular node is a bit inefficient. For now, I think I'm okay with that. Again, because I just think that correctness right now is what I'm kind of going for. So if I've got to look through the entire array to find the edge I want with a particular symbol, so be it. Now, the trickiest part, I think, for me was I need a way of firstly creating a DFA node, which to me is a little bit scary because the DFA node needs to keep track of all the NFA states that are associated with it. You know, in drawing, that's easy. I write some numbers and circle them. S1469, I just have the states written and I circle them. That's my node with these particular NFA states associated with it. That's fantastic. In code, all I can really think of at the moment is like having a DFA node be an array of integers. Like that feels. Maybe if I want to save a bit of space, I can try make them 16-bit. If I think that the number of nodes won't be too big, number of NFA nodes that is won't be too big, then yeah, I can try and use smaller integers. 8 bits I think is a bit small, but maybe 16-bit maybe can be good enough. But general idea, yeah, like literally, like I don't know what more I can do besides have an array of integers. But what I'm afraid of is if a DFA node is characterized by an array, I also, besides that, let's say that's fine. The other thing I need is a way of checking if a set of nodes already exists. That is, I shouldn't say it like that. Oh, no, that's fine. I need to check if a set of NFA nodes already exists as a node in the DFA. Because remember, one of the parts of the algorithm is if the node exists, if the DFA node exists already, then we just have to draw the edge, right? We talked about that a little bit. Like, if 10A already exists, there's no need to create another 10A state, another 10A node. I just have to draw the edge. So I have to be able to check if 10A, for example, exists in my DFA. If 10, so that kind of suggests I need like a set or a hash table kind of thing. But if the node is characterized by an array, then what? I have to apply a hash function on an array. That was my kind of conclusion that I drew a few hours ago. But I did some Googling, and apparently, yeah, that's a very practical thing that you can do. I wasn't aware of it, but I started looking at some stuff. Good hash function for an unordered set of IDs, which is what I have, right? The DFA node is a set of unordered IDs. I don't care about the order. And so there is some stuff on it. Hashing is kind of a pretty, it's kind of like an art form. Like there's a little bit of subjectiveness to it. It's not exactly an exact way of doing anything. So if I am going to do it like this, and I think I might, I think the best thing I can do is just Google a lot, maybe a bit of AI, like just see if it works, because this isn't a hashing project. Like I'm not trying to learn a whole lot about hashing, but maybe I'll pick up some stuff. I know that primes are important. I know that the size of the array being like a prime number or being like a power of 2 is like a thing, but I'll do more research on it. But yeah, I think I'm gonna need, in terms of my data structures, I'm gonna need like a hash table slash hash set for the DFA nodes, where which means like a DFA node needs to be hashed. A DFA node, which is a set of unordered IDs, needs to be hashed, which is something I've never done before. So we'll see what we can do. We've got a stack, we have a hash table, we have simple arrays for the edges. That's I'm okay with that. Then yeah, hash table for the DFA nodes now. So we have hash table for NFA nodes. Now we need a hash table for DFA nodes. I was just looking at some random stuff. And then yeah, if all goes well, then you'll see that the sort of pseudocode that I'm writing up here for my implementation is pretty much identical to what we had in the algorithm section, except specifically leveraging the data structures. So, firstly, we look at the start node, which is very easy to do because the DFA object I have at the moment has the start node in the struct. So look at the start node, find all its edges, also easy to do. Look for edges labeled with the empty string. That's because remember when I wanted to do epsilon labeling in my graph, I basically just callocked with a size of 1 byte, and then just put the null terminator in there. So completely empty string. Look for edges labeled with the empty string, and put all those neighboring nodes, plus that start node, of course, into the DFA. So that's me basically applying the epsilon closure thing. That's me applying the epsilon closure. So that's pretty cool. Put this DFA node at the top of the stack for unmarked states, or unprocessed, I should say. Unprocessed states. So this stack, And then while the stack I didn't mean to do that. While the stack is not empty, pop off the stack, getting that X, right? Same X that we were talking about over here. Pop off the stack, getting X. For each NFA node ID in X, remember X is a DFA node, which means it has NFA node IDs in it. Look up the node in that hash table, the first hash table that is, the simple one, the easy one. Get all its edges. For each symbol A, look for the edge with the edge label that matches, or look for an edge with a dot. So this is me trying to figure out how to handle the wildcard. Basically, in my mind, I need to be able to find edges that I guess can accept this particular symbol. And so the edges that can accept the symbol will be an edge that has that particular symbol labeled on it, or the dot, because the dot means anything can be associated with it. So in that sense, like any character. So look for any edge that matches that description, and then whatever that edge leads towards, put that neighboring node in the new node set. So that's for each edge. Once we've done that, apply the epsilon closure on that new node. So we created this new node set. Hang on, I did this the wrong way around. Look up. Shouldn't it be for each symbol, then for each NFA node? Hang on. Yeah, it should be the way around. Sorry. So it should be for each symbol A that. Why is it italicized? Each symbol A we care about. For each NFA node ID X in X, look up the node in the hash table and get all its edges. Get rid of this. For each edge, if it matches that, yeah, and then to the new node set, yeah, there we go. Then apply epsilon closure to the new node set to get the full version, the expanded version of the node. We talked about that. And then, yeah, if the new node set already exists in the DFA as a node Y, we use the hash set for this. Right, so this idea of the sort of fancy hash set that we care about. So check for existence. If the new node exists, then just create the edge labeled with the symbol A. Otherwise, create the new node Y. Create the new node Y before creating the edge. And then, of course, if Y has an NFA finishing in it, node ID in it, then mark Y as a finishing node in the DFA. So that's that. And that's the plan, and I took way too long explaining that, so I will go to sleep now. But that's the idea, and so, you know, as time permits, I will get onto that implementation, and hopefully I will not mess it up completely. But yeah, that's the theory, that's the ideas. That's more so just so I can understand what I'm trying to do. Get rid of all my little squiggles. Whoa, I didn't know I'd do that. But yeah, my diagrams are a bit ugly now. That's okay. That's fine. Oh, I keep doing that. Every time I try to select something, I end up. Alright, so yeah, that's the grand plan. Hopefully that made sense. And I will be doing that in the future.